Now, using our previous definition of temperature, relating energy and entropy together, it is possible for us to compare the probabilities of different things occurring by comparing their energy as well as the temperature they occur at. So this equation up at the top is our definition, thermodynamically speaking, of temperature. It actually can be shown to directly, in a system with a constant environment, as well as a relatively constant particle number, to relate directly to a comparison of probabilities. So the idea here is you'll see on the left-hand side P2 and P1. These are simply the probability of two different things occurring, or us being in two different states. This probability is always equal to the exponential, so this is E, or the exponential function, of the negative difference in energy, E2 minus E1, of these two items occurring, divided by the Boltzmann constant multiplied by the temperature in Kelvin. This here is a Maxwell probability comparison, and it's one of the more powerful techniques that comes from physics when dealing with any type of biological system, especially on the microscopic level. Because what it basically says is if you want to compare how likely things are to occur, all you really need to know is how warm is the system you're in, and what's the difference in energy between these two configurations. Now, next to this, you'll see the second equation here. This one is the normalization condition. What it basically says is if you have a bunch of different events occurring, if we add up the probability of each of these events, they should add up to 1, where 1 is something happens. This basically assumes that when we're dealing with our possible outcomes, our system is in a complete state. In other words, we know all the possibilities that could occur. Now, this type of probability-like thing is very, very common in the biological sciences. You may have seen it, solving Hardy-Weinberg style population dynamic problems. Basically, it's the same statistics. The key difference here is instead of our probabilities being measured, they can be directly predicted from temperature and energy. Now, this is a super powerful result when it comes to understanding things. The idea behind it is like, say you have a protein system with two binding sites. So this is my protein here. And there's two sites in which proteins can be bound. So what you can do with this type of system is, let's say we have things that can fill in the binding site, is you can directly compare the probability of, say, having nothing bound to the probability of having one of the binding sites filled. You can compare those probabilities again to the probability of having both binding sites built. And by using statistics, you can actually figure out, based on whatever system you're dealing with, how likely each one of these states are. And that in turn also relates to how much energy these binding events actually require in order to occur. In other words, you can actually go out and measure how likely or how many protein molecules bind to a particular protein, or how many protein substrates bind to a particular protein, and use that to actually figure out the interaction energies between these proteins and the things that, or between these substrates and the things they bind to. And that's a really, really powerful tool to have in your disposal. This probability distribution works for pretty much every physical system that occurs at a particular temperature. And if you know, for example, in this case down here at the bottom, the binding energies, you can figure out what happens if you were to take these things and put it in, say, a hot water bath in which the temperature is different. Maybe I shouldn't have used hot water bath. Let's use cold water bath so, it doesn't disappear on me. All right, so this becomes a powerful tool for not only prediction, but for the development of biochemical processes. Right? And it's not particularly difficult to use. Now, in terms of dealing with this, you'll notice here that we can have comparisons of probabilities, and we need to combine them with a normalization coefficient in order to solve for things like the probability of each event. This actually requires you to be able to use multiple equations with multiple unknowns to do so effectively. And in terms of algebra, it is one of the more involved problems that you might have to deal with. Now, the idea behind this being useful is, although we can look at it for arbitrary protein-like systems, it is actually used to find a lot of the relationships that you may know about. Don't use R is because we don't work in moles. We work in number of particles, which we'll talk about later. But you'll see this Boltzmann constant multiplied by the temperature. It shows up in these probabilities. Alternatively, if you've been dealing or been, under the impression that kinetic energy is directly related to the temperature of molecules, you can use this type of thing to deal with probabilities of kinetic energy, because kinetic energy is simply another type of energy. If you assume that your particles are just little tiny particles that don't interact with each other and are free to move in three-dimensional space, you can use these probabilities to determine the expected amount of kinetic energy that you have present in your system. Notice this still depends on this Boltzmann constant multiplied by the temperature, and this 3/2 is a mathematical constant that comes from our ability to move in 3 dimensions, the fact that our energies are defined kinetically with 1/2 mv squared, and we're using basically these probabilities in order to find the average, which is what the little bar on top of the E says. So this relationship here directly leads to a lot of the results and relationships you've used in chemistry. There's a reason why the Boltzmann constant multiplied by the temperature shows up in most of them. It's because it is present in these probability comparisons.